This is a review of multiple choice number 6 from the Chapter 7 review book, the Green and White book. You have a handout from this, and I'm going to take a look at how to do this problem. And it's also beneficial just as a review of how to attack these problems where they have a spring and they have one mass and then they change it to something else and they ask you questions about either amplitude or displacement or anything like that. So let's start off by drawing the spring with nothing on it. So there's a spring with absolutely nothing on it. And in this problem, they have a mass m attached to a spring hung vertically. So this is for vertical springs, everything I'm doing, and allowed to come to rest. So I'm going to draw that situation. And where it comes to a stop, okay, will be our equilibrium point. So go ahead and label from here, and this is how we're going to measure the equilibrium from where it was with nothing on it to here will be our equilibrium, okay, our location of equilibrium. And to get that, we can talk about the force of the spring equaling the force of the weight at that equilibrium location. So I'm going to set mg equal to kx, and x will be mg over k. So this is our force of the weight, setting that equal to our force of our restoring force of our spring. We get x equals mg over k. So this has mg over k. Now we're going to go ahead and change the mass like they say in the problem, where they add a second mass of 2m to the first mass. So now instead of this being m, okay, instead of this being m, we'll have something that will stretch more, and it now has 3m on it, so we tripled that mass, or we added 2m, sorry, we added 2m to it, so 2m plus m, 3m, same difference. So 3mg equals kx, and we get x equals 3mg over k. And that is again measured, so I draw my line here, measured from the unstretched spring to where we're at. So this distance right here will be 3mg over k. That's our new equilibrium point. We're finding our equilibrium points here. So this is equilibrium. Equilibrium. And if we don't need it, but if we wanted, we could call this the equilibrium of the first one, but it's not necessary for this problem. Now, it says that when they added that 2m to the first mass, that it was being supported, and then the support was removed, and the system begins to execute vertical oscillations with what amplitude? So when it's released from, so it started this block, this new one with 3m, started right up here in line with this one. So it started, move that dot up a little bit here to make this make sense. It started right here, and at this point it was at rest. And then it goes down, and here's equilibrium. So it's going to oscillate about this point, and it's going to start here at rest. So it's going to come down. It would keep going down here and then come back up and then keep going past the equilibrium point and come to a stop up here. So we're looking for the amplitude. We're going to go from the equilibrium to where it comes to a stop, which will be up here because of conservation of energy stuff. It'll come to stop right here because it started at rest. It's going to fall and then come back. If we look at the distance then for this, it is this, and for the amplitude, we're trying to get this right here, our amplitude. Here's equilibrium. How far up is it going to go to this point? We need this distance right here to make this a little clearer. Mg over k, that's this part. From here to here is 3mg over k, and we're looking for this. So we've got 3 minus this one. So 3mg over k minus mg over k. And we get, of course, 2mg over k, and that is the amplitude. That's not the location of equilibrium, that's the amplitude, or the distance from where it was at rest here to equilibrium. Hope that clears a few things up, and this is the process you want to follow, where you draw this, then draw the one that is stretched out initially, and then draw the new one, label your distances, and be very, very careful.